Okay, so now we're going to talk about numerical differentiation. And the basic idea, if you will, is that you're going to try to extract some approximation of the derivative of a function at a point when you only have access to the function values at a discrete set of points as opposed to the analytical expression for the function. Okay, so we're going to derive a few methods for this, and I think what's perhaps most important in what distinguishes this class in numerical analysis as opposed to a class in numerical methods is that we're going to spend a little bit of time talking about the error estimates, right? So it's not enough for you to get an expression for the approximation of the derivative. You have to have some idea as to what the error, it's like the worst case error you're making, it's like when you replace the actual derivative with this numerical approximation. So that's important. So let me just sort of state the remark that so any numerical estimate for derivatives or integrals, right, should be viewed somewhat skeptically unless it is accompanied by some bound on the errors which are involved. Okay, so for example, you've probably seen the simplest finite difference approximation of the derivative. So let me just write that. So approximation of the derivative. So one possibility is, for example, f prime of x is approximately equal to f at x plus h minus f at x divided by h. And of course, if you let h go to 0, that's obviously the usual sort of limit definition, it's like of the derivative of a function. Okay, so you can ask, what is the error you introduce when you approximate f prime, it's like by this finite difference approximation. Okay, so to assess the error, the usual way it's like you do this is to do a Taylor expansion. Okay. Okay. So how do we do that? So we know you have a bunch of points, right? You have a function and its derivative evaluated x, and then you have this x plus h term. So what we're going to do is we're going to write down an expression for f evaluated x plus h in terms of f of x and its derivatives. So which of course it's like is obtained using the Taylor expansion. So we know that f of x plus h, right, is equal to f of x plus h times f prime at x plus, so I'm just going to terminate this up to the linear term, it's like in h, and then I'll write down the remainder term, right? So the remainder, the Taylor remainder term is h squared over 2 f double prime at some unknown point. Let's call that c. So c is between x and x plus h. Okay, all right. So given that Taylor expansion with the remainder term, we can substitute it into this right-hand side and see what you get. So you have that f of x plus h minus f of x divided by h, right, is equal to f of x plus h f prime of x plus h squared over 2 f double prime at c, right? That's the expression for x, f at x plus h minus f and x, the whole thing divided by h. Okay, so fx cancels out this term. You're left with h f prime of x plus h squared over 2 f double prime of c divided by h. This is, of course, just f prime of x, which is sort of the thing you're trying to approximate, plus a remainder term, or an error term, which is h over 2 f double prime at c. Okay, so so that's telling you so that's telling you it's like the error you're making. It's like when you replace f prime with this difference, right? This kind of term here. Okay, so let me just write it in a slightly different way by moving that error term to the left-hand side and then swapping the left and right-hand sides. So that's saying that f prime of x, right, is equal to f of x plus h minus f of x divided by h minus h over 2 f double prime at cos c, right? So what we have now is the thing which you're trying to compute on the left-hand side, which you can't really do unless you have some sort of analytical expression for f, which you may not have. Okay, and then this is sort of what is called a computable approximation, right? So here we're sort of assuming that while I don't know what f is analytically, I don't have some sort of expression for it, I have something like an oracle or black box which allows me to query the function values at any point which I want. In particular, I can choose to evaluate f at x plus h and at x, and then use that to compute this computable object here. And then this thing here is the error you introduce when you replace f prime with this computable approximation. Okay. All right. So, all right. So let's look at that error term. So there are two parts in the error term. Okay. So the first part is sort of the higher order derivative term. And the basic idea, if you will, is that what this is more or less saying is that it's telling you something about how nice the function has to be in order for this finite difference approximation of the derivative to actually be reasonable. What do I mean by that? So if f is not very nice, it's not smooth, it's not very nicely differentiable, and in particular the second derivative, it's like blows up, becomes very large, then that's a problem, right? Because then this error estimate, which I'm telling you here, this error term could blow up, and so you could incur a very large error by replacing f prime with this finite difference approximation if f is somehow not smooth enough. Okay, so that's an important caveat to keep in mind, that, and it's oftentimes the case, all right, that when you get a better and better approximation, in the sense that, you know, it's like the error becomes smaller, there's also a corresponding increased assumption about the regularity, it's like, of the function. So so here it's like the error scales like big O of h, right? So which is to say that if you half h, it's like the error, it's like decreases by a factor of half, or the upper bound to the error decreases by a factor of half, right? So it's linear, it's like in the change, it's like in your discretization parameter. And it requires that the second derivatives of the function are bounded, basically. Okay. Now, what you're going to see, it's like in all likelihood later on, is that you could construct higher order approximations of the derivative, which maybe converge instead of big O of h, converges at big O of h squared, for example, which is to say that if you halve the step size, the error, it's like decreases by a factor of 4, which is you know, h squared. Okay, so so again, the problem not a problem, but it's a thing to be aware of, is that usually when you have a higher rate of convergence, there's also a corresponding higher regularity assumption of the function you apply it to. So that h squared term is going to multiply into a higher derivative of f than just the second derivative. So f needs to be smoother in some appropriate sense for these higher order approximations to be valid. Okay, so that's something which I think it's extremely important to be aware of, right? That higher order usually comes at a price in terms of an increased regularity assumption on the functions which you're working with. Okay, so these higher order derivative terms sort of force, in a sense, f to belong to a certain smoothness class. Well, at least in order for the approximation to make sense, in order for the approximation to be valid, if you will. Okay, and yeah, well, actually, I don't even need the parentheses, right? In order for the approximation to be valid. Okay. And then the second thing is the factor involving some power of h. Okay, so in this first formula which we have, we say that the error behaves like big O of h, right? So in the above formula, right, we say the error behaves like big O of h. Okay, all right. So you can construct better approximations of this. Okay, so let me sort of give you one possibility. So let's see what happens. So one possibility which you might be familiar with is sort of a finite difference approximation of the derivative, but which is symmetric, right? So instead of evaluating, so what I mean by symmetric is that instead of having the point x and x plus 1, right, x plus h, I'm sorry, you also have the function evaluations at x minus h. Okay, so let's see what happens. Okay, so to improve the formula, right, we can consider a finite difference involving data which is symmetrically distributed about the value. Sort of involving points which are symmetric about x. Okay. So the way we do this is sort of like what we've done before. We'll look at the Taylor expansions for the function at x plus h. We also look at the Taylor expansion for the function evaluated at x minus h. But both of these things, it's like expanded at the point x. Okay, so we have f of x plus h, right, is equal to f of x plus h f prime of x plus h squared over 2 f double prime at c1. Actually, I'm going to take it one higher order, sorry. F double prime of x plus h cubed over 6 f triple prime at c1. And then f of x minus h is f of x minus h f prime of x, right, plus h squared over 2 f double prime of x minus h cubed over 6 f triple prime at c2. Okay, so you've probably seen sort of the obvious candidate. It's like for the finite difference approximation of f prime and x, it's you involving these two data points, right, which is sort of the symmetric thing you get, right? Right, so this is approximately equal to, well, let me actually write down the equality. You can check that this is equal to f of x plus h minus f of x minus h over 2h. That's the computable part, right? And then there's an error term, okay, which is h squared over 12 f triple prime at cos C1 plus f triple prime at cos C2. Okay, so again, this is the computable approximation. And then this is the error term. And you could sort of see what you need to do. I mean, you can compute the error term again by, it's computing what this looks like, right? So maybe let's try to work through that. It's not so difficult. Okay, right? So you have f of x plus h minus f of x minus h over 2h is equal to, let's just look at these expressions, right? So this is f of x plus h f prime of x plus h squared over 2 f double prime of x plus h cubed over 6 f triple prime because c1, right? That's the first term, minus, okay, f of x minus h f prime of x, right, plus h squared over 2 f triple prime of x minus h cubed over 6 f double prime, right, f triple prime of cos C2, the whole thing divided by 2h. All right, so we'll see that this f of x term cancels. Okay, the second term doesn't cancel, the third term cancels. Okay, and then the fourth term doesn't cancel. So you're left with h f prime of x plus h f prime of x, right, plus h cubed. Well, actually, let me collect these terms a bit, right? So it is h 2 f prime of x plus h cubed over 6 f triple prime at cos C1 plus f triple prime at cos C2, whole thing divided by 2 times h. Right, so this is of course just f prime of x plus h cubed, or actually h squared over 12. Right, f triple prime cos C1 plus f triple prime cos C2. Okay, all right, and then just moving this to the other side gives me exactly this equation which we have here. All right, so so it's relatively easy to see that this does the right thing, if you will. This is also sort of, it's like a way to sort of think about how to actually construct these approximations, right? So if you wanted to construct an approximation of f prime of x, for example, and you know that you want to use f of x plus h and f of x minus h, right? Then you can do these Taylor expansions, okay, with remainder terms. And then what you want to do is you could assume that there are unknown coefficients in front of f of x plus h and f of x minus h. So let's say a and b. And then you take this formal combination of a times f of x plus h plus b times f of x minus h, and then you want to equate it to whatever you're trying to approximate, right? And then whatever error terms they are. So so you end up getting essentially a polynomial. It's like in h, and you want to match the left-hand side and the right-hand side term by term, and that gives you a system of equations for the coefficients, which you can then solve in order to figure out what combination you wanted to get. And this is what is called the method of undetermined coefficients. And so we'll see that maybe in a little bit. But for now, it's like that's sort of, again, just sort of a precursor to how you might actually construct one of these finite difference approximations of, say, the derivatives by using the appropriate set of Taylor expansions with remainder terms, and then sort of, choosing arbitrary combinations of these things so as to approximate the object which you're trying to approximate. Okay. All right. So, so that's the remainder term. Okay. So let's see what we can say about that. Okay, so let's assume that f is, say, 3 times differentiable. So C3, AB. Then the sort of intermediate value theorem applied to f triple prime and C, which is 1/2 f triple prime cos C1 plus f triple prime cos C2 gives me the following. Okay, that f prime of x is equal to f of x plus h minus f of x minus h over 2h minus h squared over 6 f triple prime at some unknown point. Cos C now, all right, so I'm sort of essentially combining these two terms. It's like, and then replacing it by some other evaluation of the third derivative of f, but at some other point. Okay. All right. Okay. And now C is between x minus h and x plus h, right? Okay. So, all right. So let's observe the following. So you have to be a little bit careful, right? When you're trying to approximate functions using this kind of finite difference type approximation. Because there are two sources of, actually when you're computing this in finite precision arithmetic, you have to be careful. Because, of course, there's the error term, right? Or what's oftentimes referred to as the truncation error. So this error term, you want to be as small as possible, clearly. And the way, of course, you make it as small as possible is to make h as small as possible here. But the problem with that, if you will, is that when you try to evaluate this first term, the computable approximation, in finite precision arithmetic, then when h is as small as possible, then approximating or evaluating this, it's like leads you into what is called round-off error, right? Because if h is very small, then f of x plus h is very close to f of x minus h. And so you're taking the difference of two numbers which is very small, which are very close to each other. And that has the net effect of losing the degree of precision it's like in your ability to evaluate the difference. Okay. So the number of significant digits, it's like which remain, become less and less, right, as h goes to 0. Okay, so that's sort of one problem. All right, so you should, let me sort of make the remark that the accuracy of the approximation deteriorates as h approaches 0, right, due to what is called the subtractive cancellation. And this is sort of a round-off error issue. Okay, and that's because f of x minus h is approximately equal to f of x, which is approximately equal to f of x plus h. So when you're taking the difference of two numbers which are very close to each other, the difference results in a significant loss of digits, right? So computing the difference results in loss of significant digits. Okay, and let me sort of try to illustrate this conceptually with a very, very simple example. Right, so say I have two numbers, let's say 1.0001. So here I have 5 digits of accuracy, 1, 2, 3, 4, 5. There are 5 significant digits, and I subtract off 1.0000. So these numbers are very close to each other. And what I'm left with is just 0.0001. So this is the only significant digit left after doing this difference. So initially I started with 5 significant digits in each of the two expressions, right? After taking the difference of these two numbers, which are very close together, this is the only significant digit which is left. 5 and 5 goes to 1 here, because again, these two things are very close to each other. This is the kind of round-off or cancellation error, it's like which we're alluding to. It's like in this situation. Okay, so so that's something to be extremely aware of. And in practice, what that means is that when you're using these kind of finite difference approximations, you don't let h be of the order of machine precision, right? So in practice, so I should say that in practice, right, you don't let h be like machine epsilon, right? But sort of you let h be of the order of machine epsilon, the square root of machine epsilon, right? And that choice is sort of informed by a number of things based on sort of the truncation error you have. It's like, and then based on the the sort of the model for round-off error you have. It's like, but the bottom line again is that you can't, generally speaking, take time and sort of discretization parameters. It's like which are the order of machine precision, because then you sort of bounce up against round-off error, and round-off error will mean that the evaluation of this becomes very, very inaccurate in terms of the number of significant digits which persist. Okay, so there are sort of other ways to deal with this. It's like, which I may talk about, having to do with complex derivative trick. And the complex derivative trick is kind of neat. It's like, and it involves using the fact that in MATLAB you can overload, it's like many of the standard functions, so that instead of just evaluating them for real values, you can actually evaluate them for complex values as well. So I'll talk briefly about that in the next lecture. So I'll stop now.